that has not really been addressed in physics to the extent that I think it should be. So, and also another thing is that at any point, if you have any questions, please don't hesitate to ask me. The dumber the question, the happier that I am. Because I mean, so if you ask any real questions, you might say something that is maybe not super, maybe it may not maybe sound very clever, but any questions that you have, I'm happy to answer them because the questions in this particular topic are very close to the surface. So if you ask any question, it will probably scratch something deep anyway. So it will always be useful for your audience, for the rest of the audience also, if you are brave enough to ask questions. And if I'm speaking too fast, which I have a tendency to sometimes do, just again, just remind me to slow down, and I will definitely slow down. So I don't have to get to the end of the talk. So wherever, if you have many questions and we end up going in some other direction, that's also fine. So yeah, so with that, let me just ask if you have any questions on that. If not, we can start with the lecture. Okay, so you can see the slide, right? Hello? Okay.
Yes, sir.
Okay, so let me start by saying that, so one of the basic pieces in our experience of the universe that we live in is that the future and the past seem conceptually very distinct. So a practical and experimental demonstration of this is basically that if you drop a glass of water from the table, it falls on the floor and breaks into many pieces, but you almost never see pieces from the floor on the table seating itself on the table. So you never see that. So, and this is anytime somebody runs a movie in reverse, you immediately know that it's somebody running it in reverse because our experience of how time flows forward and backward are fundamentally different. There is a qualitative difference in how we experience the future and the past. We remember the past, but we feel that the future is yet to unfold in the sense that there is a permanence that we attribute to the past that we do not attribute to the future. And so implicit belief is that one of the implicit beliefs that we have is that the future is something that has we just have to do. But this is a very subtlety enough. And the point is that in a universe governed by deterministic equations of motion, a deterministic equation of motion is essentially something like Newton's law, or if you want, you can think about quantum mechanics, all of those laws. I mean, even quantum mechanics. The Schrodinger equation, if you write this equation of motion, is that the future and the past are both equally determined. So if I give you enough data to evolve the equation at this point in time, the future and the past are both entirely completely fixed. So that makes it unclear. Why is it that we feel that there is some ambiguity about the future that we do not sense when we are thinking about the past? That's not clear from the laws of physics. So it's possible to be able to tell us why that is happening, at least at the level of the equation of motion. Okay. So this is already from the get-go. This is a confusing fact. So making sense of this apparent aspect between the future and the past is the problem of relative time physics. So why is it that why is it that we never see broken glass assembling itself into a glass of water on the table? Why is it that we can remember only the past? Why is it that the future seems unfixed in a way that the past isn't? None of these things are clear. So if you just look at the equations of motion of physics, and this is in some sense the question of what is the arrow of time. So again, I want to emphasize that if you have any questions already at this stage, please do feel free to ask, because I think it will also help me orient, because I'm just talking to a screen right now. So, and I think if you have any questions at all, it will actually will help me also to kind of orient myself. Okay. These are some basic questions about the arrow of time that one might think of just at just our day-to-day level. But there is also some seemingly distinct but ultimately closely related questions in cosmology. So cosmology is a study of the whole universe, and we have a huge amount of evidence that the universe started out from a very hot, dense state that we call the Big Bang. So the universe started out with the Big Bang, and the Big Bang was in our past. So we don't. So in the future, on the other hand, our best theories or models suggest that the universe is going to acceleratedly expand and end up in a world where all the stars have died and everything is cold and dark, and there is no light, no nothing, everything is gone, and that's the heat death of the universe. And so there's a stark difference between the future and the past when we look at the cosmological states. Okay, so when we look at cosmology, the past is definitely very different from the future. This doesn't necessarily mean that it cannot happen in a time reversal invariant theory. By time reversal invariant theory, I mean something like Newton's second law. Okay, Newton's second law is time reversal invariant, as I will show you in a second. So in such a theory, it can happen that things can, the time reversal invariance does not mean that the future cannot be different from the past. So that's another thing that I want to emphasize, and so that's the thing that I will get into in the next slide. So considering the stark asymmetry between the future and past, one might expect that the fundamental underlying time evolution laws of physics, like Newton's second law, or Heisenberg's equations of motion, or Schrodinger's equation, or these things must have some kind of built-in time asymmetry in them. So you might imagine that is the reason why we see time asymmetry in the real world around us and in the universe. But turns out that this is not the case. This is the thing that I mentioned already in one of the second slide. But this is a very important fact, so it's worth emphasizing. The key point is that the equations of motion that we see seem to be time reversal invariant. That is, if you flip the direction of time, the equation doesn't seem to change. And this looks prima facie like a contradiction. So if you look at something like this, you find that, so you might think that why is it that the equations of motion are time reversal invariant, but the nature itself is not. So to see what is going on, we'll investigate one particular case of an equation of motion or a law of nature closely. And that law of nature is Newton's second law. Because it will capture, for my purposes, Newton's second law is as good as any of the fundamental laws of nature that we might have discovered already, or the ones that we might, ones that we might discover in the future. I don't know whether they will be time reversal invariant, but I think that most scientists would bet that the laws of nature are probably time reversal invariant. So even though there are some ideas, which are contrary to that, but so generally speaking, I think the consensus would be that the most working theoretical physicists would agree that the laws of physics might be time reversal. So as a model for that, I'm going to look at Newton's second law. And as a law of nature is nothing but a differential equation. Okay, it can be an ordinary differential equation, it can be a partial differential equation, but it's always some differential equation. And solving that differential equation is, and getting some, understanding some of that equation in some way is what we mean by understanding the law of nature. So here, the first equation of motion that was written long ago by Newton is the one that I have written, equation 1. And so the key property, so the only thing that I want you to note there is that the t comes with there are two copies, dt squared is the thing that shows up there. So which means that if I reverse the direction of time by flipping t to minus t, the equation 1 does not change. Okay? So whether I go over the t or minus t, you basically end up finding the same equation. And this is one way in which you can see that this is the way in which you can see that Newton's second law is actually a time reversal invariant system. So there are other laws which have first order derivatives in time and not second order derivatives in time like Newton's second law has. So there the way in which time reversal invariance is realized might be somewhat different, but in all the cases, it turns out that time reversal invariance is actually a symmetry of all the laws of nature that we are currently familiar with. Okay, I think it's a fair statement. So yeah, so t going to minus t, you can see. I mean, is there anybody who's it's not what I'm saying is not clear? Then you can just ask me. All I'm saying is the equation of motion of the first law, Newton's second law, remains invariant if you flip the sign of t. And so the reason why this is interesting is because if a differential equation is time reversal invariant, it has a very remarkable property. And that property is that in any solution of such a differential equation, its time reverse is also a solution of that differential. So what that means is that let's say that you have a situation where you launched some, so you're looking at a particle that is falling under free fall. That's an example of Newton's law. And you started it with some initial condition, and it fell on, it moves and it reaches somewhere. And you look at the final values of the x and the t. And so the point is that if there exists always a solution whose initial data is the final data of your original solution. Okay, so such a solution can be made to evolve backward in time. So maybe I overcomplicated it. So let me just give you an example. So give me an example of what this means. Let's say we drop a ball from the top of a building and it reaches the bottom of the building with a velocity of 10 meters per second. So so it's a 1 second fall. And so the time reversal invariance of Newton's law guarantees that if we launch the ball from the bottom with a velocity of minus 10 meters per second, which is going upward, then it will reach the top of the building and come to a standstill. Okay, so come to a standstill, of course, after that it will fall, but there is a trajectory that can reach things. That's the point. So, and such a solution, so this is a fact that you can, so the fact that such a solution would exist follows just from the fact that time reversal invariance is a symmetry of Newton's second. Okay, so it is not, we don't have to know anything else about Newton's second law. We don't have to, in principle, we don't even have to solve it in detail. We just have to know that if you have a solution that does something, a solution that does the opposite is also a perfectly acceptable solution of Newton's second. So this is the basic observation, and that follows from the symmetry, a symmetry of Newton's second law, which is time reversal invariance. So, and this means something interesting for our purposes. This means that Newton's law alone cannot tell us why we never see broken glass and spilled water assembling themselves into a glass of water on the table. So, in the universe around us, in the world around us, we see that glass of water on a table falls, breaks, all that we see all the time. But the reassembly or from a broken glass, the fact that the possibility of reassembling a glass of water on the table, that in principle is a completely acceptable solution of Newton's law, but we never see it. Okay, so Newton's second law is so if you reversed all the velocities and positions of all the broken shards of glass and water or whatever, and you set it off in motion, it should in fact reassemble itself. But such a situation we never see. So the question of why is it that, so that's the essential mystery in some sense of why the past is different from the future. Because it seems like the reverse process of this does not seem to happen in nature, even though it is alone by Newton's second. Okay? So in order to understand why this reverse configuration never happens in our experience, we need to understand something more. And yeah, so I talked about, so just before I discuss that in some detail, I talked about Newton's second law here because it is the most familiar example of fundamental dynamical law of nature. So you might worry that maybe if I go to deeper physics or more fundamental physics like quantum mechanics or relativity or string theory or something like that, you might find that one of those equations might be time reversal breaking, and in which case you might actually be able to understand the future and the difference between the future and the past, the level of the equations of motion themselves. So, but that's not possible because every equation that I have ever seen, every equation that claims to be a fundamental theory that we see is basically of the time reversal invariant kind. Whether it is quantum mechanics, whether it is relativity, whether it is quantum field theory, whether it is string theory, in all these cases, the equations of motion, the laws of nature that underlie the dynamics or the nature of these things is always a time reversal invariant system. So you cannot explain the difference between the future and the past by looking at more fundamental descriptions of reality, at least not at the level that we have been able to see. So of course there are some, I should make one statement, there are people who talk about what's called finite automaton, and there they have the possibility of explicitly having time reversal invariance broken at the level of the equations of motion themselves. But these things are like at this stage they are at the level of toy models, and I don't think there is any they are, I wouldn't say that they have come up to the level of a respectable theory. So I don't think that people take them that seriously, and I think until they can reproduce the success of the more conventional forms of physics, I think it is we will not discuss. So by a fundamental theory of nature, what I mean is something, the conventional fundamental theories of nature that we are familiar with, which involves quantum mechanics and relativity and string theory or whatever it is, that is the loop quantum gravity, any of these things. So all of them are time reversible in nature. So this is the point that I'm making in this first sentence here. But there is a minor caveat, and I don't want to dwell on it too much, which is that the true invariance when relativity and quantum mechanics are taken together is something called CPT invariance, which is you have to do a little bit more than just time reversible invariance, but doesn't conceptually change the claims that I'm going to say here. So this is just a technicality as something to consider. So I will not be emphasizing. So if I just wanted to leave that there, just in case you might run into that sort of statement, because CPT invariance is a fundamentally important idea, but for the statements that for the claims that I am going to make in this talk, it will not be the distinction between CPT and T invariance will not be. Okay. So so the punchline then is that going beyond Newtonian physics alone cannot explain the origin of time as an idea, and we find that we need something more. This is the basic issue. And what is that something? Is the question. So that's something. So if this was if this was all to the story, we would have a contradiction, because our nature we know is fundamentally there is something that is distinct about past as when you compare it against future. So if our fundamental laws of nature and are time reversible invariant, and that's all there is to be said about this, then we would be in a contradiction because we are not able to explain the basic observational fact that the past is different from the future. Okay, so we will be in immediate trouble. So, but fortunately, that is not the case. So our theories are indeed capable of incorporating the difference between the past and the future and explaining to a degree the emergence of the arrow of time. So the key point is that in all of this discussion so far that I have talked about, I have not paid attention to the question of initial conditions. I did not say what initial conditions are acceptable or what initial conditions show up in nature. So this is important. So to describe the evolution by solving a differential equation, we need to specify initial conditions. While the T invariance of Newton's second law guarantees that the time reverse solution is also an acceptable solution, there is no requirement that the initial conditions corresponding to such a time reverse solution must actually show up in nature. Okay, so there is a difference between what is an acceptable solution of a law of a fundamental law, like Newton's law, Newton's second law, but it doesn't necessarily mean that has to always show up in nature. In other words, glasses with water appear routinely on tables as initial conditions in our neck of the woods in this universe. Around us, we always see that. We see that glasses with water, there is a bottle of water sitting right here next to my table, and that shows up as a perfectly acceptable initial condition in all the time in our vicinity of this universe. But on the other hand, broken shards of glass and spilled water, with precisely engineered initial conditions for the positions and velocity of all the particles so they can reassemble, never seem to appear around us as initial conditions. If they were to arise as initial conditions, yes, indeed, Newton's law would dictate that it would reassemble and form a glass of water on the table. But that doesn't happen because such precisely oriented initial conditions just do not seem to appear around us. So the question then, is, why is this so? So why is it that these certain kinds of initial conditions just do not seem to appear in our universe? And what is special about these certain initial conditions as opposed to others? So what is special about the initial condition where the glass of water is staying on top of a table? Why is it that this is the initial condition that shows up in our universe? So the second question is the easier one to answer. What makes the glass of water on a table more special? That is easier to answer, and so we will discuss it first. But a truly satisfying answer to the first question is not known. A truly satisfying answer to the first question means why is it that kind of initial conditions are the ones that we see? I don't think there is a completely satisfying answer to that question, as I will hope to convince you by the end of this lecture. So there is no contradiction. as for, we'll see that there's no contradiction. I mean, the physics works, but there is something unsatisfactory or something maybe to be understood about the nature of the arrow of time that we still do not fully understand. Okay, so the question of what is special about some initial conditions, like the one where the glass of water is on the table, was first addressed with the full gravitas reserves by Ludwig Boltzmann. And Boltzmann in many ways is the father of modern pillar of physics called statistical physics. And as you are probably aware, because many of you are mechanical engineers, you might know that this is, statistical mechanics lays the foundation of thermodynamics. So Boltzmann's primary interest was in understanding the second law of thermodynamics in terms of the physics of a huge number of particles or atoms, as they were called back in the day. And Boltzmann believes that if one knew the basic dynamical equations by which he meant the Newton's second law acting on all the particles, then by applying it to systems containing a large collection of microscopic particles, one should be able to reproduce macroscopic phenomena like the gas laws, okay, or the behavior of gases and things like second law of thermodynamics. So he was trying to derive. So instead of postulating second law of thermodynamics as a phenomenological observation, by a phenomenological observation I mean that if you have some sort of phenomenological observation underlying it, we are not deriving it from anything, and it's just an observational fact about the nature of the universe we live in, that the second law of thermodynamics holds, that entropy always increases. I will say a few more things about entropy in a bit, but I'm sure that all of you know what entropy is. So I think that word is okay. So the point is that he wanted to derive the second law of thermodynamics from the underlying laws of mechanics. This is what he wanted to do, and this program is called statistical mechanics, and it is one of the conventional tools that we use nowadays in theoretical physics. So I should make a historical aside, because despite the fact that Boltzmann was one of the most original contributions in the history of physics. And so even though the statistical mechanics is a key piece in our understanding of physics nowadays, Boltzmann's belief in atoms got a lot of instances from his contemporaries, especially from Mach and some of his collaborators. And these criticisms severely affected Boltzmann. And the story is not a good one. He committed suicide by hanging himself while on vacation with his wife and kids in a place in Italy. And that's this is the place where the reason why I'm emphasizing it, because that's the place where I did one of my postdocs, and the IISC that Ashin was talking about is in Trieste. So you have a place where Boltzmann killed himself. There is a place in Duino. It's a place called Duino in Trieste, where you can go see the place where Boltzmann killed himself. So I'm not saying that it's a place of pilgrimage, but it is a fact that some of these contributions did not come easy. So as I was preparing these slides, I was also reminded of one thing. So I thought I would make a comment about that as well, which is that, so at the time, Boltzmann died in 1906, but it was in 1905 that Einstein had his miraculous year where he wrote the four famous papers that made him the iconic figure that he is. And one of those papers had to do with something called Brownian motion. Brownian motion is the fact that if you suspend, let's say, pollen in a fluid, you can see that the pollen moves and erratically, and the erratic movement can be understood in terms of the atomic structure or the particulate structure of the fluid. This was Einstein did a mathematical derivation of Brownian motion using that particle model of the fluid. And so this was in some sense a great piece of evidence for Boltzmann's belief in atoms. But again, unfortunately, I don't think, it's a curious fact. I don't really know whether this is true, but I suspect that Boltzmann probably never found out about Einstein's calculation. So because if he had known that about Einstein's calculation, I suspect that he would have had some more confidence in believing that he was on the right track. So anyway, coming back from the historical side, a quantity called entropy was introduced. So our goal is, to set the stage, Boltzmann was interested in understanding what entropy, what the second law of thermodynamics was, what is the origin of the second law of thermodynamics was, and he understood that it was. He slowly realized that the quantity that he needs to have an understanding of is entropy. And that's for nothing but the reason that the second law of thermodynamics can be phrased as a statement that entropy can never be decreasing in any physical process in the universe. So clearly entropy is a key idea. And so in fact, one could view the arrow of time as the direction of time along with entropy increases, or is not, entropy increases, yeah. So the point, so it was clear to Boltzmann that he needed to have a microphysical understanding of entropy in order to make a statement about what the second law of thermodynamics and the arrow of time was. So this is what he tried to do. He wanted to give a statistical mechanical as opposed to thermodynamic definition of entropy. Clausius, who introduced the idea of entropy back in long ago, long before that, had a thermodynamic definition. It's a much more phenomenological definition, which means you are based on observations. But Boltzmann wanted to derive the notion of macroscopic entropy, and he believed correctly that this is what needs to be understood if we truly want to understand the mechanism behind the second law. So if you want to view second law as something more than just a phenomenological observation, and you want to understand how exactly it comes to happen, then you need to understand entropy from a microscopic point of view. Is something that Boltzmann understood. So to get a sense of what he had in mind, let's consider the example of temperature. Temperature is a much more familiar thermodynamic variable because entropy as a thermodynamic variable is quite abstract. Okay, even if you might use it all the time, entropy, what exactly does it, like at the time when Clausius introduced it, it was just a quantity that you would define in a certain way, and it is not very clear what it means. So on the other hand, so at the thermodynamic level, but temperature on the other hand is something that we have an intuitive sense for. It can also be defined purely as a thermodynamic quantity. So what you do is you say that, okay, two systems are in equilibrium if they have the same temperature, and that's one way in which you define temperature. And if you say that heat flows from one to the other, the temperature is different in some way. So, and that's one way in which you can make a definition of temperature. But it also has the advantage that we have an intuitive sense of what temperature is because it feels hot. Right? So temperature is in some sense connected to our senses in much more directly than the entropy is. But macroscopically, the entropy and temperature are in many ways on the same footing. Okay? So one is intensive and one is extensive, but that's a technical difference as far as I'm concerned. So macroscopically, temperature is another thermodynamic variable, but microscopically, it is the average kinetic energy of particles. So this was something that people had, including Boltzmann, had been able to demonstrate that the temperature of a gas, let's say, can be understood in terms of the average kinetic energy of the particles in it. So Boltzmann, in an analogous fashion, Boltzmann defined entropy as a measure of the number of different microscopic ways in which a macroscopic configuration can be realized. So what that means is, I'm sure that you have seen this, so I don't want to dwell on it too much. But the idea here is that, let's say if you have so the usual word configuration here is in the context of physics. Configuration means, sometimes it's also used, the word state is used. A state basically means a configuration where the particles' positions and velocities are both described and not just positions. That's what a state means. So configuration is usually used if you specify only the positions of the particles, but if you have a state of the particle, you have specified both positions and velocity. Okay, anyways, entropy is a number of microstates that corresponds to the same macro state. There are way more different microstates of molecules in the air, which correspond to the air being distributed all over this room than if you were to confine it to one half. So there are many microstates. So there are many configurations of air molecules which correspond to air being spread out all over the room than to just on one half of the room or one corner of the room. So this means that air being confined to only one half of the room is a macro state of lower entropy. Okay, so this is the message that Boltzmann took away from that. At least. So the advantage of making a definition of this kind for entropy is that at least part of the second law of thermodynamics becomes easy to understand when we think of entropy in this way. Systems evolve towards higher entropy because there are way more states of the system. If you start with a system where the air is confined to some corner of the room, and let's say you remove a barrier, then what happens is that the air will naturally flow to everywhere else because there is a lot more ways in which that can happen. There is a natural way in which the second law of thermodynamics becomes plausible because there are many ways to realize a macro state for a high entropy state, and so it is natural for generic evolution to take you there. So in other words, even if you start with a configuration where all the air molecules are confined to one half of the room, the moment you remove the barrier between the two halves, air molecules move to the other half. And this will result in an increase in entropy, and that is consistent with the fact that the full room has more ways of, there are more microstates for realizing air spread over the room. And this is an illustration of the second law. The latter microstate has higher entropy according to Boltzmann. The system's entropy increases in this process. And it has also become clear that it is exceedingly unlikely that the system will fluctuate back to the state where all molecules are confined to one half of the room. So, that's a highly improbable process. So if you have 10 to the 24 particles in this room, so it's very unlikely that your number of particles, will show up in just one corner of the room. Is highly unlikely. So, and looks like we have explained our second law and the arrow of time. But that's not quite true. We have not completely explained the second law fully. We have only partly explained it. This is because the second part of the question we raised in the previous slide. What this answers is the second part of the question in this previous slide. Which states are preferred? Why are some initial conditions preferred? Sorry, what is the distinction? What qualify? Let me just show you the question that I had asked there. Just flash the slide one second. So, what is special about certain initial conditions? But we haven't answered why is it that certain kinds of configurations with low entropy show up in our reactions. We haven't really answered. Yeah, we have identified what makes some initial conditions special compared to others. The initial conditions corresponding to a glass of water sitting on a table or air molecules being confined to one half of the room are initial conditions of low entropy. What we have learned so far is that given such low entropy initial conditions, it is natural that we see an increase in entropy, and this can explain the emergence of the second law and the arrow of time. But what we have not explained is that why is it that we seem to run into such unlikely initial conditions in the universe around us? This is the question that we still have not answered. Is that clear? Is there anybody there? Everybody fallen asleep? Okay, good. Sorry to make you up in case you were sleeping. So what we have failed to explain is why is it that we seem to run into such unlikely initial conditions in the universe around us? And by the way, again, at any point, asking questions is always welcome. So do not be, I can sometimes be, a bit intimidating, but do not be intimidated. I promise I will be nice. So what we have failed to explain is why is it that we seem to run into such unlikely initial conditions in the universe around us? Okay, any questions at all? Any questions? Yeah, absolutely.
Sir, can I ask you something? Sir, if the past and the future was the same, or the law governing it would be the same, would the Big Bang or the start of the universe be relevant?
Yeah, so I mean, see, that's what I was saying, that, even if the equations of motion have time reversal invariance, you can have, you can have changes in time. So for instance, Newton's laws are time reversal invariant, but it allows changes of things with time. Right? It's not that's what we are saying. The time reversal invariant does not mean that the solutions of the equations are static. That's not what it means. It means that if given a solution with changes in time, there also exists another solution with changes in precisely the opposite. That's what it means. So, for example, in the universe, the universe could be a solution to the fundamental equations of motion, but as long as those equations of motion will also allow another universe which is contracting. Does that make sense? So the question of why are we in the expanding universe is a question which we do not have an answer. But the fact that we are living in an expanding universe is not inconsistent. Does that make sense? Yeah. So the point is that you can have both kinds of solutions. It is not that the universe is static. So time reversal invariant does not declare or dictate that the solutions of these time reversal invariant equations have to be static. That's not what it says. What it says is that you can have change with time, but any solution of the equations which changes with time will also allow a solution which changes in the it will also allow a solution which changes in precisely the opposite. So if for whatever fundamental theory we have, if it allows an expanding universe, it should also allow a contracting universe. So that's all it says. So the question of why we are in one as opposed to the other is something that we don't really have an answer. Okay.
So, sir, will there be anything in between a contracting and an expanding
Yeah, I mean,
universe?
many such solutions are. Yeah, I mean, so you know, so there are solutions. So the question, what precisely constitutes a theory is a slightly tricky question. So yeah, I mean, in principle, yes. So there are. It doesn't have to necessarily be. So for instance, there are solutions that people have envisaged which expand contract back, and you know, they there is something called the bouncing universe scenario where you have like the contraction, after that there's an expansion, and but it a little bit it depends on what precisely you are, which precise equations you're working. So I think that as solutions of standard general relativity, all of these solutions are zero. So perfectly in the sense, yeah, with some minor caveats about what kind of matter will be there in this universe. So given those minor caveats and tweaks as solutions of general relativity, they are all perfectly acceptable. So a universe, whenever you say cosmology of a universe, what you really mean is some solution of Einstein's equation. So Einstein wrote down an equation whose solutions contain, cosmologies. So yeah, so that's slightly technical, but yeah, what I said is correct in the sense that you can have expanding, contracting, bouncing, various kinds of universes. So it's kind of like the one way to understand it. It's not as some people get disheartened by that. So let me clarify what exactly that means. So for instance, if you have Maxwell's equations allows solutions where the entire universe is filled with an electric field. We don't see such a solution. Okay, so a theory is supposed to give us the solutions that we encounter in nature, but it can have solutions which we do not encounter in nature. There is nothing wrong with it, because a theory is supposed to be able to explain all the things that we see, but it can also have solutions which are just not there. So if we don't have if we don't, the case where the entire universe is filled with an electromagnetic field is a perfectly acceptable solution of Maxwell's equations, but it just does not happen to be the case that is the universe that we live in. So it's the same sort of an idea that the kind of universe that we are seeing is not so there are many solutions to equations of motion, and which solution is the one that we call our universe is depends on many things.
Okay, because so there will be another universe in which the glass of water, the chunks of glass will come back to the table, but that will be another universe where the direction of time will be in opposite entropy level.
So I don't think we have a meaningful way of so at the level of the universe, even if the universe starts contracting back, the arrow of time will still be, the entropy will always still be increased. So so yeah, I mean maybe you can ask this question a little bit later. What exactly is the question? I think that I have not said enough yet to properly orient that question. So maybe you can ask the question again.
Okay, sir. Thank you so much.
Yeah. So so the point is basically, it's kind of related to this question, which is that what we have explained is that we can there exists natural configuration with low entropy, and if we start with the low entropy initial condition, Boltzmann and the second law of thermodynamics, and we ensure that there will be a natural arrow of time and entropy will increase. Okay, so that entropy increase is a natural thing if your initial conditions are such that they are of low entropy. But the question is, why are the initial conditions of low entropy? Why do we find so many low entropy initial conditions is unclear. So that's especially because of the fact that if you randomly pick some configuration in the set of all configurations, you would actually find that you're overwhelmingly likely to pick a configuration of high entropy, because high entropy means there are many such configurations. Okay, so it's unclear why exactly is it that we have our initial conditions um, seem to have a lot of low entropy initial conditions. So it just seems kind of like an accidental fact of nature, and I don't think there is a fully satisfactory answer to the question. Some people might say that this doesn't require an answer, and that's a valid standpoint. You don't, because initial conditions, we don't necessarily have to have a theory for our initial conditions. But as I will try to motivate, there seems to be something going on here which I think we have not fully understood. So, okay, so our universe seems to be a system far from equilibrium. That's another way of saying it. So if you're in equilibrium, if you're in global thermal equilibrium, you are in the maximum entropy state, maximum entropy macroscopic state. So when you're far from equilibrium, on the other hand, you're no longer in maximum entropy state, and evolution will slowly keep pushing the entropy higher and higher towards global equilibrium. So the reason why anything at all happens in our universe is because of this fact. Okay? Because if you're living in complete thermal equilibrium where everything was thermalized, you would not see any kind of action. It will just be, once in a very very long time you might see a fluctuation, but very very long time means it's many orders of magnitude higher than the age of the universe. So, but other than that, you would not see anything. It would be just like just be a barren wasteland. So so what we know about entropy and the second law also means one more thing. The entropy of the universe was lower yesterday than it is now. Okay, because so this fact, because of the statement about the second law of thermodynamics, this is a natural extrapolation. And if we extrapolate all the way backward, we come to a very interesting conclusion, which was the beginning of the universe, the Big Bang. That's an exquisitely low entropy state. So it was a phenomenally fine-tuned, extremely low entropy, very, very fine-tuned state with low entropy, and that's where our universe is begun its expansion. So this is our universe in some ways, at least based on this kind of arguing. If you think of the universe as an isolated system, if you think of the universe as an isolated system, which it may not be. So if you think of the universe as an isolated system, it's an exceedingly improbable initial condition is where it started. Okay, so note that there is no contradiction. I'm not saying that this is not consistent with the law of nature. It's consistent. It's perfectly consistent to have whatever initial conditions that you want. That's as long as the initial conditions themselves are consistent. It's a perfectly valid choice. We do understand. We have an understanding. We understand why the origin of the arrow of time. We understand why is it that we live in a universe where there is an arrow of time. It's because, as I just said, our universe started out in a very special state at the Big Bang. Okay, and but the only thing is that it's a kind of an unsatisfactory answer. We are simply not satisfied with the answer we have found because we would like to know why the universe started at such a highly special initial condition. And this is usually an underemphasized fact, I think, even among in the physics community. I think that even among, let's say, I'll say a few things about it. I think the fact that the universe is extremely fine-tuned is not something that the initial conditions of the universe are extremely fine-tuned. It's not something that is appreciated often or emphasized often. So this is so a situation where we have no sharp contradiction, where there's no problem. We don't have to worry about it. But we get the nagging sense that the nature is pulling a fast one on us is what is called the fine-tuning. And the idea that the universe started out in this very early entropy, very low entropy initial state is sometimes called the past hypothesis. Okay, so this is what truly makes the past different from the future. And in fact, even though I would not have time to go into it, this is what gives us the illusion that we can remember. Well, this is what helps us. This is what is responsible for we being able to remember the past and we not having the ability to predict the future. And at the same time, so for instance, the illusion of free will, all of these things are kind of connected to this idea that the idea that the universe was started out from a highly fine-tuned. So, and the Big Bang is the mother of all fine-tuning problems. So, and the reason why I say that is because in physics we have a few other fine-tuning problems, and if you have some interest in physics, you might have heard of something called the Higgs mass hierarchy problem or the cosmological constant problem. I'm not going to tell you what those things are. If you have questions on them, you can ask them later. But so for my purpose of the talk, it's just sufficient to know that there are some problems which are fine-tuning problems in physics, and these fine-tuning problem is related to so for example, the fine-tuning problem related to the Higgs mass is roughly a fine tuning of 1 in 10 to the 17. And the one related to the cosmological constant, I mean, depending on how you define that, is 1 in about 10 to the 30. Sometimes people write it as 1 in 10 to the 120, but that's, I think, slightly misleading. So 1 in 10 to the 30. But the fine tuning required by a creator, a metaphysical creator, let's say, in order to have made our universe, is estimated to be about 1 part in this humongous number. And this is a stunningly and shockingly huge number. This is something that, so essentially what you're saying is that in the set of all allowed initial conditions, you would have had to pick it with this much precision so that we end up where we are. This is what this estimate is really telling us. So the initial condition of the universe, if we want to have the relentless, ongoing arrow of time for the 13.7 billion years that the universe has been in existence, then the fine-tuning required is this much. This is a crude estimate. I mean, I have not really followed the estimate completely closely, but it's a huge number. Is all that finally matters. And this is an incomprehensibly large number. And I want to emphasize that the universe is stunningly big, stunningly big. I don't think we really can form an opinion or a realistic understanding of any sort of how big the universe is. And this number beats any number of that we have in this universe. For instance, our galaxy has 100 billion stars. Billion is 1,000 million. So we have 100 billion stars, and there are 2 trillion such galaxies just within our particle horizon, within our visible universe. Just within our visible universe, there are 2 trillion such galaxies, and each galaxy contains 100 billion stars. So it's a humongous universe, but none of these numbers compare to this humongous number that we are seeing here, which is understandable since the arrow of time is really what is responsible for everything that is here on this. So let me emphasize this point a little bit. So a lot of people, even practicing physicists, often carry the impression that Big Bang was a situation close to global thermal equilibrium. And this is a completely wrong assumption or belief. This is partly because the phrase Big Bang, when you hear the word Big Bang, it conjures up visions of a messy explosion and leading one to imagine that it's a high entropy state. But it is not, as I will argue in the next slide. It is also because of the fact that, so this is a slightly more technical comment, if any of you are, interested, is that it's many of the calculations that one does, you assume that the matter in the early universe was approximate local thermal equilibrium in order to do the calculation. So, and this is a valid and approximation, but that's not quite the same thing as saying that the universe itself, the global state of the universe, was close to maximum entropy. That's not the case. So if you assume because of these reasons that the early universe was in a high entropy state, then that is very wrong, because it's just not the case. And the reason for that, and there's a very fundamental and important reason why people make this mistake, is because they forget a very key player in the early universe, and that's gravity. Okay, so gravity is the fact that the things are collapsing, expanding, whatever. So because everything is so compressed together, the gravitational physics that is relevant at the early universe is you cannot ignore it. For systems with gravity, a roughly uniformly distributed gas of matter is not the highest entropy state. For example, you might think that if you have a box of gas, okay, the gas, just like in my room that I was discussing before, spreading the gas everywhere, spreading the air everywhere might be the most high entropy state. That's a very reasonable guess. But this is not the case if you have gravity. And the reason for that is that gravity any gravitating system has a natural instability towards collapse. And this instability is sometimes called Jeans instability. And so that means that whenever you put up gas of stuff in a finite, let's say finite volume, and the highest entropy state, or even if it is not a finite volume, it doesn't really matter. It will always be local gravitational collapse will always happen. So even if it is, even if it is not in a finite volume, so it has a collapse from black holes. So the puzzling thing, so whenever you have a gas that is distributed in a gravitating system, it always has a tendency to collapse. So the puzzling thing about the early universe is that despite the fact that the most entropically favored state for the matter in the early universe was a collapsed black hole. So that's what it should have been, given the fact that there was so much gas in the early universe. So we find instead that the matter was extremely uniformly distributed at the Big Bang. Okay, so instead of finding a black hole, if considering the fact that there was so much matter and all of that was compressed at the time, we would have expected to see a black hole of the initial condition of the universe, in which case we would not see any universe at all because it would not exist. But that is not what we find. We find that the universe was, the early matter was very uniformly distributed at the early stages of close to the Big Bang. And again, I want to emphasize this is not quite a contradiction. It's just an initial condition at the end of the day, but it's just a shockingly improbable initial condition for a gas of matter, for a distribution of matter. So yeah. So I don't know whether I explained that well. If you have any questions, you can ask me. But again, feel free to interrupt. Okay? So I might, as I get, if I get excited, I might speak faster. So that's something that I have to kind of worry about. Okay. So and just as a side comment, in fact, I'm sure that some of you must have heard of the cosmic microwave background. Cosmic microwave background is a radiation that's coming at us from all directions in space with temperature of around 3 Kelvin, and it's basically the afterglow of the Big Bang. So you can think of it as, the Big Bang was very hot, and whatever was left, like if things cool down later on, very roughly speaking, you can think of it as the burning embers of the Big Bang. And you can see that by looking at the microwave background, we can actually see that the original gas distribution, the matter distribution at the beginning of the Big Bang was extremely uniform. So, and it turns out, so let me not get into the discussions about these details here that I'm kind of bored of mentioning, but maybe it's already we are getting past time. It turns out these measurements show that indeed the early universe is extremely homogeneous and isotropic. Homogeneous and isotropic means the matter that time was very uniformly distributed, and that's exactly what this CMB measurement, that is called microwave background observation, demonstrates. So the question is there a theory or a paradigm or an idea that one can use to understand why the entropy of the early universe was so small? Okay, so this is something that we would like to understand. As far as I know, there is not. So there's no real setup where we have a systematic way of understanding why is it that the entropy of the early universe was so small. So just to be technically somewhat precise, there is an idea called cosmic inflation, which suggests that, which gives you a reason or a mechanism why the universe became very homogeneous and isotropic. Homogeneous and isotropic means everything is inflated. Okay, so why did it become that? So there's a mechanism that inflation gives you, but the mechanism is not sufficient to explain the problem of initial condition, problem of low entropy of the initial condition. Because even if inflation happened, you still have to explain why is it that initial condition for inflation was so fine-tuned that we got it. It only makes it worse. So inflation is not an explanation for the entropy problem associated with the things that I'm talking about. There are many other things for which inflation is a good answer, but it is not a good answer for this question. So in the next slides, what I'll say, I'll just end with just one speculation. So, because this is not like something that, is much discussed about. So in the next slides, I'll just leave you with a brief speculation that might be relevant for understanding the entropy question. Okay, so and after that, I'll conclude my punchlines or whatever, so that you have a few take-home messages. So ideas that I'm going to discuss have some similarities to give credit where it is due. There are some similar ideas that occur in the works of Tom Banks and Krishnan. Also, Samir Mathur has some interesting ideas in this direction. And a paper by Naoki Sasakura also has some similar things. So I'm just giving you the names, it doesn't matter. But the philosophy that I'm presenting here, I don't think is quite the same as theirs, and I don't think it is really been widely appreciated. Anyway, so the key observation that I want to start with is that a uniformly distributed gas is in fact the highest entropy state in a world without gravity. Okay? Indeed, this is the reason I emphasized that point earlier. So if you have an initial matter that we have in the universe, if we did not have gravity, what we are looking at the early universe is basically the highest entropy state of the system. But the trouble is that, of course, we also have gravity. So if there was no gravity, it is immediately clear that the initial conditions of the universe are precisely the most natural, unfine-tuned, high entropy ones. Okay? And this raises the possibility that perhaps Big Bang should be viewed as the switching on of gravity in some sense. Once gravity is turned on, the system of gas, which has a high entropy state, ceases to be a high entropy state and instead becomes an extremely fine-tuned state. And this is because now the gravitating gas, the highest entropy state, is not a distributed gas, but it's a collapsed black hole state. So suddenly, the system that you're starting with, if you somehow manage, if there was no gravity in the early universe, at least before the Big Bang, there was no gravity in the early universe, then what we have, the dense, the hot Big Bang, which contains this matter that is very evenly distributed, is a high entropy state. So there's no contradiction or no surprise regarding regarding how it became so high. And if you have a dynamical mechanism somehow which can turn on gravity, then then that I think can explain the problem. So is there some way in which to make the speculation into a reasonably concrete model? It's not very easy because we lose control of a lot of the things that we do when we get closer to the Big Bang, and we don't fully understand. I mean, we do understand things surprisingly more than many people realize, but we do understand things quite well. Starting probably about a second after the Big Bang. So the very early parts of the Big Bang are still kind of mystery, and it's hard to make a fully consistent model that respects all the things that we already know about the universe, which matches with this kind of thing. So, and it's a kind of even though it might seem like a simple idea, this is, as far as I know, this is not really has been really looked at, and it is not very it's not very easy to realize also. So what is the take-home message? So this is essentially my last slide. So what are the take-home messages? So the fundamental laws of nature are time reversible invariant. So this is one thing that I think, as far as we know, this is the thing that I kind of want you to kind of take away. That the laws of nature that we see around us, the fundamental laws of nature that we know, are basically time reversible invariant. They do not distinguish between past and future. But on the other hand, the world around us and our experience of the world around us has an asymmetry between the future and past, which is one of the most obvious things about the physical universe. And just these two simple facts lead us to a pretty remarkable statement about the early universe, that the universe started out as a very special state. While this is not in contradiction with anything we know, it does leave us with the feeling that there is something deep that we are missing. So, and that's where I'm missing. When I see any questions. Thank you. Any questions?
Thank you, sir. The query QA session can be initiated, and students who would like to question about the topic can do that, please. Sir, there's a question from my side.
Okay.
Like, using this fourth dimension as time, can we bridge future and past?
You mean like, yeah, so I mean, there are like some recent ideas about the possibility of building wormholes, for instance, in our own universe, there is a possibility that we can, in principle, have wormholes. So we can go to the future. We can't go to the past. So wormholes that we are building, if they satisfy some basic consistency conditions, like the energy in the universe cannot be negative, and that seems to be a fundamental constraint. And energy, like the energy of matter cannot be negative. The energy of matter is not negative. Then we can build. There is a possibility. There is I would say, not an impossible possibility. There is a fairly reasonable possibility, even though technology might take a long time to catch up with it. So there is a realistic possibility of building a wormhole, at least for small size wormholes. So the problem is that the wormholes that we are so far able to build, or we have even the possibility of building, are wormholes connecting very short length scales. They are not really like macroscopic length scales. If you want to go to Proxima Centauri, it's not really very useful. But if you want to, as a mathematical idea, there is the mathematical, as a possibility, it certainly exists that you can construct wormholes of a certain type in our universe. So, or at least it seems very plausible to me that that's not impossible. But the only caveat is that if your hope was going to plan to go back in time, yeah, that I think is unlikely.
Okay, sir. Thank you.
Okay, hi, Chethan. Jude here.
I think there are two questions simultaneously. I think you can ask it one by one. Yeah.
Hi.
Jude, hi. How are you?
Hi. Yeah, I'm fine. How are you?
Good, good.
Yeah, so regarding the speculation that you said in your talk,
Yeah.
that the Big Bang should be viewed as the time at when the gravity sort of switched on.
Yeah.
Okay. In many ways, people also study black holes as in some sense being the inverse of the Big
Right.
Bang, right? In the sense that they are both the extremes and there are singularities present at each of the. So, can a similar speculation apply to black holes as well? Like
It's
as one
possible.
approaches the singularity.
It is possible. Yeah. So and
Okay.
so it's so also another thing that I want to say is that there is a sense in which yeah, this is a slightly technical remark because you know so the question is a slightly advanced question. So I'll ask slightly advanced answer. So which is that so if you have so for instance if you're talking about for instance you can go well I mean let me answer this question in when we talk. So I don't want to intimidate students in the silence.
Oh, okay. Okay.
We would like to know how you found your interest in all this physics and string theory and everything.
I was actually not initially very interested in string theory. I mean, I wanted to do physics. I wanted to do theoretical physics, but you know, I made the mistake of going to IITs to do engineering. So then I switched to physics. But the reason why, but I was initially not very interested in string theory. It seemed like too speculative to me at the time. But over time, as I studied it, I became more and more convinced, or maybe more and more, you know, programmed into believing that string theory is a good thing. So either way, I mean, I think that now there are many aspects of string theory which I think is really kind of, you know, it's a good toy setup for studying these questions. If we know that string theory is a consistent theory, so we can ask various questions with it, which is what makes it an interesting one. Because many other theories that we have, they're in many ways they're incomplete. They are like there is various things that are already that we know. Like for instance, we believe that quantum mechanics, a theory that we trust should satisfy both quantum mechanics and relativity. This is something that we believe because these are extremely well tested principles. Okay, so you can't really break one of them and then do some model, and then it's not really interesting for anything. So string theory's greatest advantage is that it doesn't sacrifice quantum mechanics or relativity or general relativity, and at the same time you can ask questions regarding gravity with it. That's what makes string theory very interesting because it's an excellent toy model for asking questions about what might happen. It's a good toy model for doing thought experiments. So that's what I mean. Yeah. So my answer to the question of why I got interested in string theory is eventually it's very slowly that I got interested in string theory. Yeah, and I think anyway my interest in physics I would say is broad. Like it is not like I don't want to kind of just say that I'm a string theorist. You know, yeah.
Okay, sir, thank you.
Any other questions? Any question is fine. I think the more honest the question, the more I think the people will get out of it. So do not be, you know, do not worry about it. So I think there was one question that was asked earlier, which I guess I don't know whether it was whether I fully answered it or not. But yeah, please feel free to ask questions.
So no questions means shall we wind up the session?
Yeah, sure.
Uh,
Thank you
so
very much.
is there anyone else to ask the questions? Like one last question. No, I guess. So thank you, sir, for doing this presentation for us.
Yeah, so thank you. Yeah, thank you very much.
And ASME MACE is honor to have you in our Spectrum 2020, sir. Thank you.
All right. Okay. So shall I sign off?
Sure, sir.
Thank you very much.
Thank you, sir.
Thank
Thank
you,
you,
sir.
sir. Thank you,
Sorry?
sir.
Yeah, thank you. Thank you very much.
Will you teach on NPTEL?
Sorry?
Will you teach on NPTEL?
Oh, do I teach at NPTL?
Yes.
No, but so if, I think that I strongly recommend Professor B. Balakrishna's lectures in NPTL. So he covers all the fundamentals, I think, better than I took his courses when I was in I was there in IIT. So I took his physics courses. So he is a fantastic lecturer, and I sometimes watch those lectures before I go give lectures. So I think they are, like, because he has a way of speaking which where all the subordinate clauses all come together, sentences are complete, everything is perfect, which is very difficult to pull off even if you, yeah. So, but yeah, his lectures are fantastic. So on many things, mathematical physics, statistical mechanics, quantum mechanics, all of those, he has many lectures on NPTEL, which I think all of them are fantastic. So you can take them.
Okay, sir. Thank